So before we got to this unit, the shapes of graphs that we've learned so far are the line, which you guys should know already from Algebra 1. We talked about the parabola shape, that was from Unit 2, right? And then at the end of last unit, do you guys remember we were doing stat edit, stat calc, and I briefly introduced that cubic and quartic shape to you guys? We're going to be talking about that more in detail this time. So we're going to learn how to graph them, how to analyze them a little bit more deeply. So those are called polynomials. So that's what we're going to be working with in this lesson, in this entire unit, really. So a monomial. A monomial is an expression with one term. Hence the mono, one. A term is basically another word for it is like a piece of an expression. So a monomial, we have several examples here. A monomial can be a number, a variable, or a combination of the two with multiplication. So as long as you don't have anything with addition or subtraction, you're not adding or subtracting anything, it's just one term, that's considered a monomial. So we have 27, 12x, negative 3.5xy. All of these are connected with multiplication. That makes it one term instead of a string of multiple terms. 16xy squared, negative 77m cubed n to the fifth. What are some examples you guys come up with for monomials? 8, just 8x?
One of them's 8x.
Okay. What else? What's another one that you could come up with? What's an interesting one?
15
over 3? That's not interesting.
Sorry. Listen.
What else? What's another one? What else? Be creative. What's a monomial that you guys can think of? Neither of us was giving me too many examples to write down. You guys are like crickets. Come on, what's an example of a monomial? You guys quiet because you don't understand what a monomial is, so I need to re-explain it.
Square root of
Okay. No variables? Okay. There. Makes it more interesting when you have variables. Here. So literally anything. You can write whatever number, whatever variables, whatever exponents you want. They could be positive, negative, decimals, not. As long as there's nothing being added or subtracted, you don't have a string of multiple terms, that's considered a monomial. Then we have a polynomial. So that's what we're going to be focusing more on in this unit. A polynomial is an expression with multiple terms connected by addition or subtraction. An expression with multiple terms that are connected by addition or subtraction. So the kinds of equations that we've been factoring and solving, those are all polynomials because we have different terms, several different terms, and then they're being strung along or connected by these operations of addition or subtraction. That's what makes it a polynomial. You have more than one term. Technically, monomial is still considered a polynomial. It's just a polynomial with one term. But polynomial in general is going to have an extended list of terms that are connected. We also have specific types of polynomials. So how many terms does this one have? 3. That has a specific name. Do you guys remember? Trinomial. And if it has 2 terms, binomial. So monomial, binomial, and trinomial, those all have specific names. Anything that has 4 terms and beyond is just generic polynomial. Okay? Alright, so this one is a polynomial, this one is a polynomial. Can anybody else come up with an example of a polynomial? Creative, anything you want, as long as it's a polynomial.
We're divided by 2x plus negative 2 over 6.
That would be a linear, or a binomial here, a linear function. Again, as long as you have more than one term, it's considered a polynomial. Or even a monomial is, but more consistently we call polynomials things that have one term. Alright, this is a pretty important box. We talked about standard form before, but only for quadratic functions. Polynomial standard form has the same idea as with the quadratics. So a polynomial has as many terms as you want, but it's only going to be in standard form if the terms are arranged by degree in descending order. I'll explain what degree means. It basically, whatever exponents you have, if you have like a squared, and that's the biggest exponent you have, that needs to come first and then needs to decrease from there. So, like this one is in standard form because it goes x squared, x, and then no variable. Remember, it's in decreasing order. That's true for any polynomial. So you can see that for this one too. 5, 2, 1, nothing. It's in order, decreasing. So that's a really important concept to remember, what standard form of a polynomial in general looks like, because you need your polynomial to be in standard form in order to do analysis a lot of the time. So don't forget how to arrange that in standard form. Now, a couple of vocabulary words. Leading term. So leading term is the term containing the variable of highest degree. The term containing the variable of highest degree. Degree is basically describing the exponent that it has. So the leading term is going to be the entire term, including the coefficient, of the exponent, or sorry, the variable that has the highest exponent. So for example, if I was looking at this one up here, the 4x squared plus 9x minus 8, which exponent is highest there? Exponent. Which of these has the highest exponent? In this function.
Oh, four.
This one right here, right?
Yeah.
So this would be considered the leading term. Whichever piece has the highest exponent, that entire piece, that term is called the leading term. Now that's why it's important to write it in standard form. When it's in standard form, the leading term will be at the front. If it's not in standard form, that could be anywhere. So that's why it's really important, especially when they jumble up everything where it's not in standard form. You guys need to remember the leading term is whatever contains the highest variable or degree. It may or may not be in standard form, so don't just assume it's always at the front, because if they don't write it in standard form, it won't be at the front. Okay? It should be if they write it correctly, but if they jumble everything up, then it won't be in the front. You're just looking for the highest exponent. Alright, so the degree of your entire function is the highest exponent value. Highest exponent value. So if I ask you to write the degree of an expression or function, all you have to do is find the biggest exponent and that's it. Again, the degree represents the highest exponent value that you have in the expression. So if I look at, this is referring to up here, so if I look at example A, what would the degree be? No, degree would be the exponent's value. 2. The degree is 2. Whatever the highest exponent's value is, that is the degree. So if the highest exponent you see is a 2, then the degree is 2. What about this second example? It's 5. The degree is the highest exponent. 5. What about this one that we made here? It's 1. Because the highest exponent that I have for the variable is a 1. So that's how you find the degree of a polynomial. Okay? Leading coefficient. So the leading coefficient is the coefficient of the leading term. That's why they both have the word leading, because they're kind of referring to the same thing. Now there's an important thing to know between these, because I always get kids mixing these up. The leading term is the entire term. It includes the coefficient and the variable. So when I ask you for the leading term, I want you to say the whole thing, like 4x squared. That's the leading term. But if I ask for the leading coefficient, that's just the 4. Does that make sense? The term is the whole thing. The coefficient is just the number in front. Does everybody understand the difference? Okay. So if I ask for the leading coefficient of example A, what would it be? Leading coefficient would be 4. What's the leading coefficient of example B? -3, because that's the coefficient of the leading term. And then what would the leading coefficient be for example C?
3 divided.
Yeah, 3/2. Right? So leading term is the entire piece, the entire term that has the largest exponent in it. So it's the entire thing, the number and the variable together. But the leading coefficient is just the number. Is everybody clear on that? And anytime I ask for a degree, that's just the highest exponent that you see, whatever that number is, write it down. Is everybody good with that? Okay. Then we've talked about end behavior already, so we're just going to reemphasize that again. So end behavior is where the arrows point on the ends of your graph. Obviously, this is the least technical way to define end behavior, but it's how we understand it. So it's where the arrows point on the end of your graph. We're going to have a left arrow and a right arrow. Okay? So we've talked about all 4 different types of end behaviors, but just for the quadratics that we've been working with so far, what are the 2 possible sets of end behavior for parabolas, for quadratic? Nope, you can't. Think of a parabola. Think of a parabola. Where could the arrows be pointing for a parabola? So, yes, but how would you, like, what are the direction words? Like, if your arrow is pointing, okay, so direction words are down and up, but for our parabola, it looks like this. What's the end behavior? Up, up, right? So we've already learned about one type of end behavior, which would be up, up, so both of the arrows are pointing up. What about the other type of parabola?
Down,
Down,
down.
down. So the ones that we've seen in application so far, more often than anything else with our quadratics, was up, up, and down, down. But there are other combinations. What are the other combinations you could get? You could get up, down, or down, up. So there are 4 total. There's no more than this. There are 4 total possibilities for end behavior, and you guys are going to need to be able to recognize what the end behavior is by looking at a picture or by just looking at the equation. What we've done up until this point is just looking at a picture and seeing the end behavior, which is really easy. You can see, oh, that's pointing down, that's pointing up. Now what you guys need to be able to do is just look at the equation and be able to figure it out. And I'm going to show you how to do that in a second. But just a quick reminder, when you guys are writing notation, you guys will be writing end behavior and words and in notation. Don't forget that to say left, it's x approaching -infinity. And then you guys are going to do y approaching something. Just going to leave that blank because we don't know whether it's positive or negative, it's going to change. And then on the right side would be arrow, x arrow infinity, y arrow, whatever for your graph. So don't forget, yes?
Put the notation symbols.
Say again?
Do you put like the notation symbols?
Yeah, I'm leaving these blank for now because again, it'll change depending what your graph is. I'm just reminding you guys this is what the setup would look like, and then you'd fill in these blanks depending on your graph. Okay? Alright, so this is your little key for being able to look at a polynomial function and be able to tell what end behavior it has. So it's based on the degree and the leading coefficient. Those are all you need to see. Right? So everything comes from the leading term. You're going to find the degree, which is the biggest exponent that you have. If that degree is even, so 2, 4, 6, 8, an even number or something, it's going to behave like a parabola. Okay? So for a parabola, remember that the end behavior were going in the same direction. So they're either both up, up, or both down, down. So if your degree is even, they're going to be going in the same direction every time. Okay? The question is, how do you know if they're going to be going both up or both down? And that's where you look at the leading coefficient. If it's positive, which way do you think they're going to be going? Okay? So if it's even and then positive leading coefficient, you'll be going up, up. It's like a happy parabola. Because when A was positive, you had the 1A, 3A, 5A going up. So if you just think, if you see an even number, think parabola. If it's positive, up, up. What if it's even and it's negative? Down, down. Okay? So whenever you think even, think of a parabola. Picture a parabola in your head. If you see an even degree, whether it's 2, 4, 6, 8, whatever it is, picture a parabola in your mind. If it's a positive parabola, that's up, up. If it's a negative parabola, it's down, down. Okay? However, if your degree is odd, so it could be 1, 3, 5, 7, anything like that, if your degree is odd, they're not going to be the same, they're going to be opposites, which is like a line, right? A line has opposite directions. So whenever you guys see an odd degree, whether it's 1 or not, imagine a line in your head. What kind of end behavior does a positive line have? From left to right? Down, up. I like to think of it this way. If it's positive, you should be rising. And you can only rise if you start down and go up from there. Okay? So if it's odd positive, you're going to be rising, so you start down, go up. But if it's a negative line, up, down, it's falling. So if you're a memorizer, you can just memorize this chart and you can write it for yourself on an assessment or something and just use that. But I am a more conceptual thinker, so if you're conceptual, just think if it's even, it behaves like a parabola. They should both be going in the same direction, either happy or sad, right? So think of that in your head. And if it's odd, it behaves like a line. They're going to be opposite. If it's positive, it's rising. If it's negative, it's falling. Okay? That's how we're going to be finding end behavior for polynomials based on the equation on the picture. Last vocabulary word for you guys is turning point. So it is a point where a graph changes direction. Point where a graph changes direction. Hence turning. It's basically, it's literally a point where the graph turns. It could be going up and then it turns to go down. The point where it does that is a turning point. Now, so you guys need to know the definition, but you also need to know another rule that follows along with turning point. I may ask you how many turning points a function has just by looking at the equation and not the picture. Now, the way that you're going to do that, you guys can tell me the greatest possible number of turning points. You can't tell me exactly how many, but you can tell me the maximum. That is going to be 1 less than the degree. Okay. So if I give you a polynomial function and I want to know what the maximum number of turning points would be, you would just take the degree of the function and subtract 1.
So that's 60.
Yes. So if your polynomial's highest exponent is a 6, then it has 5 possible turning points. So think about a parabola. If I have a x squared plus bx plus c, what's the degree of a quadratic? What's the degree of a quadratic? 2. So what's the greatest possible number of turning points? 1. That's why it looks like this. It only changes direction once. Okay? So I changed it to a cubic. What's the degree? Degree. The degree is now 3, so what's the greatest number of turning points? 2. So it could look like this. However, it could be less, right? So that whole trick here, the 1 less, tells you the greatest possible number. So the greatest possible number would be 2 turning points, but you could also have 1. It could be less. That's why you can't actually tell me the exact number of turning points for a function unless you actually graph it. So you'll see the wording of the question is going to say what's the maximum number, not the exact number. You can only figure that out by graphing. So again, for the cubic function, you could have 2, but you could also just have 1 if it's shallower. Okay, so that's something to make sure you keep. All right, let's go ahead and apply this on the next page. So I have several functions here. We're going to answer these questions that we were just talking about, like the degree, the maximum number of turning points, the leading coefficient, end behavior, that kind of thing, all based off of these functions that we are not going to graph. Read the door, please. Alright, so our first function here is f of x equals y. That's the same thing as, f of x equals 5. That's the same thing as saying y equals 5. Remember that f of x and y are the same thing. What would this line look like if you graphed it? It'd be horizontal, right? So we're going to have to be careful as we think about this one. What would the degree be?
Isn't there no degree?
What's technically the highest exponent? 0.
Oh.
Remember that anything that has an exponent of 0 turns into a 1 and kind of just disappears. So there's like an invisible x here with an exponent of 0. So the degree is 0. What would the leading coefficient be? 5. That's really the only number we have to work with. So 5 is the leading coefficient. Alright, what's the maximum number of turning points?
0.
How do you find the maximum number of turning points from the degree?
The degree minus 1.
Say again?
The degree minus 1.
Okay, but what's the degree?
0.
What happens if you subtract 1?
Negative.
Can you have negative 1 turning points? No. So this one's not relevant. Sometimes, depending on what your function is, if it's overly simplified in terms of monomials especially, sometimes these questions can't be answered. It doesn't really apply to that type of graph. What about end behavior? You guys can draw a little sketch if you want to kind of see what we're looking at. So this is a horizontal line. What kind of end behavior would that have? Anybody? Up, down, up, down, down. What do you think?
I don't know any up or down.
Is it going up?
No.
Is it going down?
No.
Does it have end behavior?
No.
This is another one where it doesn't really apply. If it's flat, you can't really say it's going up or down. Alright, next one is linear. What's the degree of this linear function? 2x plus 3.
1.
The highest exponent for a variable is 1. I know you can't see it, but anything that doesn't have physical exponent written is 1. What's the leading coefficient?
2.
Alright. What would the maximum number of turning points be?
0.
0, and that should make sense, right? Because a line never changes direction. It just goes whoo, forever in one direction. Or both directions infinitely, but it doesn't bend. Alright? Okay, so now this is where you guys have to think about the end behavior. Think about that chart in your head. This is an odd degree. Okay, so they're going to be the end behaviors are going to be opposites. And it's positive. It's positive 2. So imagine this is a line, but imagine a line that's positive. What would the end behavior be? Down, up. This is rising. It starts down and goes up. So this end behavior would be down, up. I'm just going to abbreviate. So if that's what it is in words, how would I turn it into symbols? X approaching negative infinity is which side of the graph? Left. So then on the left it's going down towards negative infinity. And on the right it's going towards. So make sure you know how to use the words and symbols. Convert back and forth. Alright, next up is quadratic. What's the degree?
2.
2. The highest exponent is 2. What is my leading coefficient?
1.
Okay, so now again, think carefully. This is an even degree, and it's positive. So when it's even, they're both going in the same direction, and it's positive. Up, up. Oops, I forgot this one. What's the maximum number of turning points? Sorry about that. 1. 1 less than the degree. And then the end behavior is up, up. So then what would I write for both of my y's?
Positive infinity.
Okay. Everybody okay with that one? Yes? No, they don't. That's what we're talking about. There are situations where they're different. Alright, cubic. What's our degree? Careful.
3.
3. Our degree is 3. The degree is the highest exponent, and the highest exponent there is 3. Okay. What about the leading coefficient? It's not 2.
Maybe 1.
It's negative 1. What's the leading term? No. What's the leading term in this expression? This at the front? No.
The variable would be highest.
The leading term is the term that contains the variable with the highest degree. I've warned you guys about this. They don't always write them in standard form. Just because this is at the front does not necessarily mean that it's the leading anything. Okay? It just means that they didn't write it in standard form. You guys need to be on the lookout for that scenario because that's how they're going to trick you. They're going to expect you guys are going to be rushing, lazy, I don't know. But you're just going to go for whatever you see in the front. And that's not always going to be the leading term, leading coefficient, whatever. So look for the degree, that highest exponent. And it's a good idea. I personally like to do this if you find it to be helpful. Go ahead and circle it. When you find the number or the highest variable, circle that entire piece, the entire term. That thing that you circled is the leading term now. So you get all of the important information from that. So you circle this, and so the leading coefficient is -1. How many, or what's the maximum number of turning points? 2, which is 1 less than the degree. All right, so now we have to think end behavior to memorize that chart. Remember, because we're not allowed to graph this. So if we have an odd, we have odd for the degree and it's negative. So when it's odd, that means that they're going opposite directions, but it's negative. It's falling. So it's up, down. You can think odd, opposite, they both start with O. Alright, so on the left, Y is approaching positive, but on the right, negative. Okay? Alright, so what about the quartic? What's our degree? It's the highest exponent. 4, so I'm going to go ahead and circle that entire term, just to remind you what the leading term is, because all the information comes from that. So if our degree is 4, what's our leading coefficient? -1. Maximum number of turning points? Yep, you're right. 1 less than the degree would be 3. And then our end behavior. So our degree is even, 4, which means they have to be, if it's even, they're the same, and it's negative. Down, down. Alright, so on both sides of the graph, Y is going towards what? Right, I will give you a second to do these last two on your own. Alright, who has the responses to this row right here? Who'd like to share out what they have?
Sis?
Okay. Oh. Oh, okay.
Negative.
Okay. Everybody get that? The leading term, again, was out of order, so you can circle it to make it stand out so you know what you're working with. What about this next one? Anybody have that? Hi guys, you go. Okay. Alright. Positive to negative. Right. Leading term is right here. Oops. Again, out of order. Just look for the highest exponent to know which one would be the leading term. Alright, is everybody okay with that analysis process? Any questions? Okay, now we're going to revisit increase, decrease, and domain and range and kind of tie all that together. We're going to be doing the same kinds of questions, but now in reverse. So this time I want to know the information based off of the graph and not the equation. So we have to approach it slightly differently. Sometimes it's easier, sometimes it's not. But again, we have intervals of increase, decrease. We've talked about this already, so it shouldn't be brand new. Right? The increase, decrease intervals are going to switch off at turning points. Previously, we've called turning points hills and dips. You can still call them that if you want to, but basically anytime you go up to the very tip top of like one of those hills, that point up there is called a turning point, and that's where we would change between increase or decreasing depending on whether you're going up or down. So we're going to use the exact same thinking that we've done before. Remember that we use the x values to write these intervals. We use the y values to see if they're actually increasing or decreasing, but the interval that we're giving is based on the x values. Okay, so remember the highlighting and all of that we did to help support that. We're going to do the same kind of thing again. So looking at this first example, what would the domain be? We've done this before, you guys have seen it on your spirals. So what would the domain be for this function, this cubic function? Okay, we're going to use both notations. So in set notation, it would look like this, right? What about interval? So do you guys see? I know I accidentally cut off the arrows just because of the way I cropped the picture, but both of these sides of the graph go on forever, right? It's understood. If it goes to the edge of the graph, it's going to continue going. So they go left and right forever. What about the range?
Y plus R.
Real numbers, all real numbers is a better way of saying that. Right? Do you guys see how it's now going down and up forever too? You see that? So both the domain and the range are going to be all real numbers. Alright, what are my x-intercepts? This is something else you guys already know as well. What are my x-intercepts in this picture?
1 and 0.
How do you write an x-intercept?
X equals
-2, 0,
1 and 0.
and 1, 0. An x-intercept is a point, everybody. So you're writing them as points. And what about the y-intercept? 0, 2. Sure you write that as a point as well. Anytime you see intercept, it's a point. Alright, now here comes the questions that we were talking about today. They're a little bit new. How many turning points does this graph have?
2.
2. This kind of question is visual. Before we were finding the maximum number of turning points, which is not exact. We were just subtracting one from the degree because we couldn't see the picture. This one we can see it is exactly 2 because we are visualizing the picture. We can see it represented for us. Now if I know that I have 2 turning points, what would my degree be? Why?
You add.
Because we're doing this concept backwards, right? If you know the degree first, you subtract to find the turning points. If you know the turning points, then you add to find the degree. It's forwards and back. It works both directions. Okay, so if I have 2 turning points, that means the degree was 3. Now, this is where it gets a little bit tricky. I want to know, if I were to write the equation, what kind of leading coefficient would I have, positive or negative? What would I use from the graph to figure that out? The end behavior. Remember how up here the relevant because it helped us find the end behavior? Now we're going to go in reverse now. So we need to know the end behavior first from the visual and go backwards to find the leading coefficient. So what's the end behavior for this graph? In words. It's down, up. So you see how it's rising? What kind of leading coefficient gives us a rise?
Positive.
A positive. If it was flipped, so it started up and then it went down, that would be a negative relationship. So you can use the visual and the end behavior to pick it apart to get back to the leading coefficient. Alright, so in notation, let's go ahead and write the end behavior in notation. So on the left, we have x approaching negative infinity. On the left side, which you'll write in notation, where's y going?
Negative infinity.
It's also going towards negative infinity because it's going down. Okay? But then on the right, when you have x approaching positive infinity, where is y going?
Positive.
Positive. So it's a good idea to write the end behavior in words first and then translate that into your symbols. It'll help kind of cement that idea in your head. Alright, now we're going to do increase decrease. So if you guys remember the strategy that we use for increase decrease, you're going to use colors and you're going to use vertical lines to chop your graph into parts. So we're going to take a vertical line at each turning point, your hills and your dips. You draw a vertical line for each turning point, and then you're going to label them with whatever number that is on the x-axis. Okay? So what number would this one be on the x-axis? What number does it go through? 1. And then what does this go through?
Negative 1.
Okay? Then you also label infinity and negative infinity to set the stage. Then your colors come in. Okay? Highlight rising, rising, and then the x-axis that corresponds with those. And then you're falling, and the x-axis. Remember the color coding, all this stuff that we did before? Alright, so let's start with increasing. What color is increasing? Sorry for anybody who's colorblind. What color am I using to represent increasing over here? I'm using the red, okay? So I'm going to represent the red portion of the x-axis as an interval over here on this line. So what's this first interval? It starts at negative infinity until, so my first interval is negative infinity to negative 1. Is that the only section of my graph that is increasing? No, so that means I have to write a union symbol to jump over the gap. Then where does my next red section start?
1.
And then it ends at positive infinity. So all these things that we did at the very beginning, labeling everything, those are all that you need to write the intervals. And then what about the green? From what to what is decreasing? Negative 150. I'm going to write it over here. Negative 1 to 1 is your decrease. It's coming back. We've done this before, so you guys should know how to do this. I wrote it over here because it wasn't writing correctly, but that's the interval of decrease. Great. Let's try the next one. What would the domain be for this guy? For this left, for this right? It'd be all real numbers again. Get in the habit of writing both notations every time. So you never know which one they're going to want from you, so just practice both. And then what about my range? Is that all real numbers like the other one? Does it go down and up forever?
Negative 9.
Okay, so what's the lowest number that you see? It's cut off right here. Oops. Imagine that's kind of where it stops. There we go. That's at negative 9. Now what direction does it go in compared to the negative 9? Up. So when I write my range, it's going to be y such that y
Y is
greater than or equal to. Remember, your set notation uses inequalities. And then for your interval notation, you have the bracket around the negative 9 because it's equal to, and then positive infinity. So you read from bottom up. Okay? So in this next one, I have 4 x-intercepts. One of them, I'm just going to write them down because it's pretty easy to see. One of them is negative 3, 0. Then we have negative 1, 0, 0, 0, and 2, 0. Everybody agrees with that, right? We have this one, this one, this one, and this one. Sorry, 4. What's my y-intercept? 0, 0, right? How many turning points do I have in this one? 3, which means the degree would be 4, which you should connect with from last unit because our quartic functions, which look like W's or M's, have a degree of 4, high school number of 4. Would my leading coefficient be positive or negative if my end behavior is up, up? It would be positive. Because with an even degree, to get the end behaviors to be the same, it has to be a positive leading coefficient. So on the left, when you write your notation, x approaching negative infinity, where is my y going? On the left, positive infinity. And then when you write your notation for the right, x approaching positive infinity, y is still going to positive infinity. Alright, now we're going to do our increase, decrease, just like we've done before. This picture is a little bit crowded, so I'm not going to draw the vertical lines. I'm just going to write the numbers at the turning points. So this one right here, that line is at negative 2. This one is at, unfortunately, it is a decimal. So that one right there is approximately negative 0.5. This one is at 1. And then we have infinity and negative. That's the first thing you want to do, is label those vertical lines if you draw them. Or at the very least, write down the x value at the turning points. And then we're going to use our colors to color code. the increasing bits and the decreasing bits. Alright, so for increase, which I've again coded in red, on my first section here, from where to where am I increasing? -2 to -0.5. Use only the numbers that you guys have put into the picture. That's why I did that first, so I can really easily piece everything together. So that's this little red section. Then what's the other red section? It starts at 1 and then goes to positive infinity. Oops, you cannot see that. Right? Everybody okay with that? Alright, what about decrease? The green section over here, where does it start? Negative infinity until -2. That's the first green. And then where does the second green pick up?
-0.5 to 1.
So hopefully you guys remember the increase decrease stuff and that kind of clicks. Alright, so that's where we're going to stop.